Okay, so question 5 was all about circular motion. And so in this case, we had an amusement park ride and the person is moving around like this, and it wanted us to draw and label a free body diagram for 2 marks. So I go up to thinking of it and I look at this and I go, okay, well, the person is obviously they're pushing back against the side's pushing back against them. So our normal force in this case is the one that's pointing towards the centre. So that's our centripetal force. But you must label it as the normal force. You can't label it as centripetal force. We're still going to have the weight pulling the person down, but what's stopping the person from sliding down is the friction with the end of the container, or the surface, sorry, I should be saying. So the friction up there. So we wanted weight and friction to be balanced, okay, and then normal perpendicular to the surface in there. It then was asking a show question for a couple of marks. So in this case, we know that N is the centripetal force. Okay, so if I'm giving it in terms, I'm looking here, they're giving it the angular, so I'm going to give the angular version of this. So M omega squared R, which we've taken from the data booklet. At this point, I also remember that friction force is equal to mu N, which is also equal to mg, okay, because remember the friction and the weight were equal, but I can also give my friction in terms of the normal, and that's where we can get that mu coming in there. So in this case, my friction force is mu N, so mu omega squared R, which is equal to mg. Can cancel my m's out. I get omega squared is equal to g over mu r, so omega is equal to root g over mu r. Okay, so it's a nice little show. They do give us show questions in the IB that aren't ones that we've seen before. Okay, so something that I hadn't seen until this question as well. It came out in the latest paper that was done. So it is a difficult one, but you have to be able to solve these equations, and it's testing your physics knowledge here. The next part then was then asking you to use this equation. Actually, you could do this different ways. We were saying just deduce, so you have to prove with maths whether they will slide or not slide down. And again, it's 3 marks here. So I'm going to show you 2 ways to do this. The first of them is working out the angular velocity, so the omega, okay, and seeing if it's greater or less than it. If it's greater than it, then they're not going to slide. So I can calculate it for what it would be. So this is omega is equal to 9.81, so I'm using the equation back up here. So 9.81, mu is 0.4, and then r is 3.5, and that's 2.6 radians per second. Now, I know that the speed at which their person is moving at is omega is 2 pi over t. Now they're moving at 28 revolutions per minute, so I want to put that into radians per second. So in this case, that's 2 pi over 60 over 28, which is 2.9 radians per second. So their angular velocity is greater than it's required, so they did not slide. So I could use that way as one method. So that was kind of like option 1. Okay, option 2 was actually using the friction force. If the friction force is greater than the minimum amount, then they would stay the same. So I looked at the minimum friction, so friction force, it was equal to mg, because remember up here we said they're equal to mg. So that's just m times 9.81, so 9.81 m. So that's the minimum friction force required. So I'm now going to look at the real amount of friction force. Okay, so that was mu omega squared, m omega squared r, so 0.4 times m times, again before, having to do that 2 pi over 60 over 28 squared multiplied by 3.5. So just using all those up again, having to work out that angular, angular velocity. And then in this case it was 12m. Remember, this is not meters, this is just 12m. Okay, that's mass. So 12 lots of the mass, which is greater than 9.8 lots of the mass. So the friction force is increased. So again, she's not going to slip. Oops.